Welcome to the deep dive, everyone. We are so glad you could join us today.
Yeah, thanks for tuning in.
So today, we are looking at something that honestly sounds like it's straight out of a sci-fi movie.
Oh, absolutely. It's wild.
Right. But the crazy thing is there are actually hundreds of millions of these things just in our galaxy alone. We are talking about neutron stars.
Which is just a fascinating topic.
It really is. And the source notes for today take us to the extreme limits of physics. So our mission here is to just kind of take our time, keep it at a relaxed pace, and break it all down together.
Yeah, you definitely don't need a physics degree to marvel at this stuff.
Exactly. We want you to be able to just sit back and, enjoy the universe. Because the scale of this topic is just mind-bending to me. Like when we try to imagine something incredibly heavy, our brains usually go straight to sheer physical size.
Right, like a massive boulder.
Yeah, or a skyscraper. Or, I don't know, an entire mountain range. We
Yeah.
inherently link mass with volume. We assume that to be heavy, a thing just must be huge.
Which makes perfect sense here on Earth. I mean, our entire biological intuition is built around that relationship.
Right.
But step out into deep space, astrophysics, and that intuitive rulebook gets completely shredded.
Oh, totally.
Imagine taking an object vastly heavier than our entire sun, like a million Earths worth of mass, and physically crushing it into a sphere so small you could drive across it in half an hour.
It's absurd. We're talking about a sphere roughly the size of a city, like Sydney or Melbourne, but the matter inside is packed so tightly that a single teaspoonful weighs about 1 billion tons.
1 billion tons.
Yeah, it's the mass of all humanity, or like a Himalayan peak squished into a teaspoon.
It's hard to even picture.
It really is. But to even begin to understand an object this extreme, we can't just look at the finished product, right? We have to look at how it's born.
Yes, the origin story.
Because you don't get something this dense without a spectacular, incredibly violent origin story.
You really don't. I mean, a neutron star doesn't just gently form from a cloud of dust.
Right.
It is the corpse of a massive star,
Huh.
forged in one of the most cataclysmic events in the universe.
So to understand that death, we first have to look at how a star lives.
Exactly. A star spends millions of years in this constant high-stakes standoff between two opposing forces.
Right, let's visualize that standoff for a second.
Mm.
So gravity is relentlessly trying to crush the star inward under its own immense weight.
Mm.
And the nuclear fusion in the core, which is basically just the star burning its fuel, is pushing outward.
Right.
And instead of the usual balloon analogy everyone uses, where the rubber pulls in and the air pushes out, I actually like to picture a submarine diving deep down into the Mariana Trench.
Oh, that's a great way to look at it.
Yeah, so you have the crushing weight of the ocean pressing in on the hull that's gravity, and inside you have the pressurized air and the structural integrity pushing back out. As long as that internal pressure holds, the submarine survives.
That captures the tension perfectly. In a star, that outward pressure is generated by the core fusing lighter elements into heavier ones.
Like burning hydrogen into helium.
Exactly.
Yeah.
And then helium into carbon, basically just moving up the periodic table. And the energy released by this fusion is the pressure holding that submarine intact against the crushing weight of its own outer layers.
Okay.
But, a star has a finite energy budget. Eventually, the core fuses elements all the way down to iron.
And iron is a dead end for fusion, right?
It is the ultimate stellar ash. Fusing iron together doesn't release energy. It actually absorbs it.
Oh, wow.
Yeah, so the moment a massive star's core turns to iron, it basically goes bankrupt. The fusion engine shuts off. The outward pressure just vanishes.
So the submarine loses all of its internal pressure in an instant.
In an instant.
And gravity, which has been patiently waiting for millions of years, suddenly has zero opposition.
None. Gravity takes over completely in a state of literal freefall. You have a core that might be millions of miles across, and it collapses down to a sphere just a few miles wide.
That is terrifying.
And this doesn't happen over years or even days. It happens in a fraction of a
A
second.
fraction of a second.
Yes. The core falls in on itself so incredibly fast, and with such horrifying force, that the outer layers of the star rush inward, hit this newly condensed, unyielding core, and violently bounce back.
And they blast off into space in a supernova explosion.
Exactly. Which is so profoundly bright, it can briefly outshine the entire galaxy it sits in.
Okay, let's unpack this. Because the outer layers blasting away just leaves us with that crushed core. If we strip away the supernova explosion part, what is actually happening to the physical matter inside that core when gravity runs completely rampant?
Well, to see that, we have to look at the microscopic structure of matter.
Okay.
As we know, an atom is overwhelmingly empty space. The source notes used a really good analogy for this. An atom is basically a tiny, dense nucleus surrounded by a vast electron cloud far, far away.
Like a fly buzzing around in the middle of a massive cathedral.
Yes, exactly like that. Usually the electromagnetic force keeps those electrons in their orbits, maintaining all that empty space. But the gravitational pressure of this collapsing core is so unimaginable that it physically overwhelms the forces holding the atom together.
So it's like taking a colossal stadium built out of scaffolding, and instead of taking it apart piece by piece, you just apply so much pressure from the outside that the metal struts buckle and the whole thing gets compacted into a solid block of steel.
It's a perfect visual. Gravity looks at all that empty space inside the atom and simply claims it.
Wow.
The crushing force pushes the electrons so hard, they are violently forced straight into the protons within the nucleus.
Wait, they just merge.
Yeah, they merge, neutralizing their charges, and become a neutron. And the core is undergoing this transformation on a macroscopic scale.
Every single proton and electron.
Every single one gets fused together. The entire object becomes a swirling, unimaginably dense ocean of pure neutrons, packed shoulder to shoulder.
Packed shoulder to shoulder. So you essentially wind up with a single, gigantic atomic nucleus the size of a metropolitan city.
That's exactly what it is.
Which completely explains that mind-bending density we talked about earlier. You haven't added more stuff to it. You've just entirely deleted the empty space that makes up normal reality.
Yes, you forced matter into a state it desperately does not want to be in.
Yeah, I'll bet.
And this brings us to a precarious new standoff. Gravity wants to keep crushing, right? To compress the star down to a single point of infinite density.
Right.
But the neutrons themselves push back. Through this quantum mechanical principle known as neutron degeneracy pressure, the neutrons basically refuse to occupy the same quantum state.
So they just push against each other.
Exactly. They create a final, stubborn physical barrier against gravity.
But it's hovering right on the brink, isn't it? Like
Yeah.
if you have something that massive squeezed that tight, if the original star had just a little bit more mass, or if the core captured a bit more material on its way down.
Then the neutrons would fail.
Oh, man.
Yeah, gravity would win that final battle too.
Hmm.
The degeneracy pressure would be overcome, and the core would collapse infinitely, tearing a hole in space-time and creating a black hole.
That is just so wild.
A neutron star is literally the absolute densest physical object that can exist before breaking the universe's rules entirely.
It's the universe taking matter right to the precipice and stopping just a millimeter short of the edge.
Exactly.
But, you know, if you take a massive stellar core and abruptly shrink it down to a city-sized sphere, it can't just sit there quietly, right?
Definitely not.
All the momentum, all the energy from that massive star, it has to go somewhere. Like, I'm thinking of a washing machine on the final spin cycle.
Oh, that's a fun comparison.
When all the heavy, wet clothes get pinned tightly against the center drum, you know, the mass concentrates and the machine spins terrifyingly fast. The whole thing hums with this aggressive rotational energy.
That is conservation of angular momentum playing out at an apocalyptic scale.
Right.
Apply that washing machine logic to a stellar collapse. The source notes talk about a figure skater pulling their arms in to spin faster.
Oh, yeah.
So you have a massive star that was rotating slowly, maybe turning on its axis once a month. But as it collapses, pulling its mass inward, it has to conserve that rotational energy.
So by shrinking from millions of miles wide to just a dozen miles wide,
The rotation speeds up exponentially.
so a star that used to take a month to complete a single rotation is now spinning, what, several times a second?
Far faster than that in many cases. Some of the fastest known neutron stars are spinning hundreds of times every single second.
Hundreds of times a second.
Yes.
Try to actually visualize that. A sphere heavier than our entire sun whirling around in deep space faster than the blades of a high-speed kitchen blender.
It's almost incomprehensible.
The centrifugal forces trying to rip it apart must be staggering.
Oh, they are. Only the extreme gravitational grip holds the physical material together. But the spin also triggers another wild transformation.
Okay, what's that?
Well, stars naturally have magnetic fields. When the core collapses, those magnetic field lines are dragged inward and crammed tightly together.
Right, because everything is shrinking.
Exactly.
Yeah.
And this extreme compression amplifies the magnetic field to a level that defies comprehension. We are talking trillions of times stronger than the magnetic field here on Earth.
Trillions. A magnetic field that's strong, spinning hundreds of times a second, has to turn the whole thing into a massive cosmic dynamo.
It really does.
Hmm.
It creates an electric field so potent it actually rips charged particles directly off the surface of the neutron star.
Wow.
And these particles are accelerated along the intense magnetic field lines and blasted out from the star's magnetic poles at near the speed of light.
That's insane.
It creates two blinding, powerful beams of electromagnetic radiation shooting out into space.
Like a cosmic lighthouse?
The comparison is remarkably apt. Because the magnetic poles of a neutron star rarely line up perfectly with its axis of rotation, those beams sweep through space in a massive circle.
So they're sweeping around like the beam from a lighthouse.
Precisely. If that neutron star happens to be angled just right, one of those beams will sweep across Earth with every rotation. Our radio telescopes don't see the star itself in visible light. They just detect a brief, intense burst of radiation. Then nothing. Then another burst.
Flash, flash, flash.
Exactly.
Sweeping past us again and again
Yeah.
with the cold regularity of a metronome. You know, I think my favorite part of this whole phenomenon is how we actually discovered them.
Oh, the Jocelyn Bell Burnell story.
Yes. Back in 1967, Jocelyn Bell Burnell, who was this brilliant graduate student, was poring over literal miles of paper data from a radio telescope and noticed the strange, incredibly regular ticking signal.
She observed pulses arriving exactly 1.33 seconds apart.
And the signal was so unnaturally precise that it genuinely baffled the astronomical community, right?
It did. Natural objects weren't supposed to keep time like that.
The researchers actually labeled the signal LGM on their charts, standing for Little Green Men.
Yeah, they half-jokingly wondered if it might be an alien beacon.
Because what else in nature could possibly act like a perfectly calibrated clock?
But of course, it turned out to be the sweeping beam of a rapidly spinning neutron star. Today we call these specific objects pulsars.
Great.
And what's fascinating here is how these clocks turn neutron stars from a wild mathematical theory into a confirmed, observable reality. They are among the most precise natural clocks in the universe.
Wow.
Their rotation is so deeply reliable that astronomers utilize pulsars to test the most complex theories of physics, including Einstein's theory of general relativity. They just measure minute changes in their ticking over years of observation.
So what does this all mean? We've got these incredibly dense, ultramagnetic washing machines deep in space, acting like lighthouses and ticking perfectly.
Right.
It paints a picture of an isolated, lonely sentinel in the dark. But the notes say this connects to something in my pocket or on my finger. How? What happens when two of these cosmic lighthouses end up crossing paths?
That is where the story shifts from isolated physics to the creation of the universe's most precious materials.
Okay, I'm listening.
Many stars exist in binary systems, which is basically two stars orbiting a common center of mass.
Right, like a pair.
Yeah. If both of those stars are massive enough to end their lives as supernovas, you can end up with two neutron stars locked in a binary orbit.
Two of these blenders orbiting each other.
Exactly. But it isn't a stable, eternal dance. Over millions or billions of years, as they whip around each other, they lose orbital energy, their orbit gets tighter, and they inch closer and closer together.
Until they eventually collide.
Yes.
Which, incredibly, we actually managed to witness in 2017. Two neutron stars in a distant galaxy spiraling in and smashing together.
It was a monumental day for astronomy.
I remember. Telescopes caught the flash of the collision. But wait, if this collision happened in a distant galaxy, a telescope seeing the flash makes sense. But the astronomical community also talked about how they felt or heard it happen.
Yeah, that's the wild part.
How on earth do you feel a collision from another galaxy?
By detecting ripples in the actual fabric of space-time itself, known as gravitational waves.
Gravitational waves.
Yes. To understand this, imagine standing inside a massive enclosed bell tower when a gigantic bronze bell is struck.
Okay.
You don't just hear the sound with your ears, right? The sheer acoustic energy is so intense, it shakes the air, and you physically feel it rattle in your chest.
Oh yeah, I felt that.
Well, space-time is the medium of the universe. When two unimaginable masses like neutron stars slam into each other at a significant fraction of the speed of light, the violent displacement of mass strikes the fabric of reality like a hammer.
It rings the universe like a bell.
Exactly. It sends waves of gravity rippling outward in all directions at the speed of light.
Wow.
And when those waves finally washed over Earth in 2017, highly sensitive instruments called LIGO detected the actual stretching and squeezing of our planet.
The planet itself stretched.
Yes, but by a tiny amount, a fraction of the width of a proton. But we felt the impact through gravity, and mere seconds later, our optical telescopes saw the flash of light as the debris glowed.
And it's the debris from that collision that I find absolutely fascinating, because a normal star, even a massive one, maxes out at fusing iron, like we said earlier.
Right.
But when we analyzed the light from that neutron star collision, we found the chemical signatures of much heavier elements being forged in the wreckage, things like platinum and gold.
Yes.
Why does smashing two dead cores together force atoms to build gold when the raging inferno of a living star's core cannot?
It comes down to a process called rapid neutron capture, or the R process.
The LAR process.
Yeah. Creating an element heavier than iron requires an enormous input of energy, but more importantly, it requires a massive surplus of free-floating neutrons.
Okay.
In a normal star's core, there simply aren't enough loose neutrons around. If a nucleus manages to capture a neutron, it usually undergoes radioactive decay and breaks apart before it can capture another one.
So it's like trying to build a tower out of wet sand, but the sand keeps sliding away before you can stack the next handful.
Exactly the problem. But in a neutron star collision, you are literally smashing together two city-sized balls of pure neutrons.
Right.
The collision releases a flood of hot, dense, free neutrons into the surrounding space. It is a completely chaotic environment.
I can imagine.
Lighter atomic nuclei in the debris are bombarded by these neutrons so rapidly that they capture dozens of them in a fraction of a second. The nuclei are built up incredibly fast, vastly outpacing their natural decay rate.
The tower is built so quickly that the wet sand doesn't even have time to collapse.
Exactly. They stabilize into the heaviest elements on the periodic table.
Wow.
The universe produces a vast amount of its platinum, uranium, and gold, not in the bellies of ordinary stars, but in these specific violent cosmic collisions.
Yeah.
The gold we mine from the Earth's crust did not originate here.
It came from space.
It was forged in the fiery wreckage of crashing neutron stars billions of years ago, seeded into the gas clouds that eventually formed our solar system.
Here's where it gets really interesting for you listening. If you are wearing a gold wedding ring right now, or a gold chain, you aren't just wearing an expensive rock.
No, you're not.
You are physically wearing the shrapnel of dead stars. You are wearing a tangible piece of a cosmic catastrophe that predates the existence of our planet.
If we connect this to the bigger picture,
Yeah.
it fundamentally changes our relationship with the materials around us. They aren't just rocks in the ground. It bridges an incredible gap between the abstract, unimaginably vast phenomena of deep space and the mundane objects we touch every single day.
It really does.
The heavy metals in our technology, the jewelry on our hands,
Yeah.
they are the literal aftermath of stellar tragedies playing out in the dark abyss.
It makes you feel small, but in a deeply awe-inspiring way,
Absolutely.
And it's worth pausing to appreciate just how incredible it is that humanity can deduce any of this. I mean, we are sitting here detailing the precise density, the magnetic field strength, the rotation speeds, and the elemental fallout of objects that we will never, ever be able to visit.
Objects we can barely even resolve visually. Most pulsars and neutron stars appear as nothing more than faint points of light or abstract data points ticking across a screen.
Just a flash on a chart.
Right. Yet by meticulously observing those flashes of radiation, by building machines sensitive enough to feel the microscopic ripples in space-time, and by relentlessly applying the laws of physics, we have managed to reverse engineer their secrets.
We've basically turned them into the ultimate natural laboratories. We use them to test how matter behaves under extremes of pressure and gravity that we could never hope to safely reproduce in a laboratory here on Earth.
They push the boundaries of physics to the absolute breaking point. But, it is also critical to acknowledge that our models are not complete.
Right.
There are genuine open questions that astrophysicists are actively wrestling with right now.
Like, what exactly happens in the very center of the core itself?
Precisely. We understand that the outer layers of a neutron star are composed of this incredibly dense fluid of neutrons. But as you travel deeper towards the dead center, the pressure reaches a peak that our current mathematics actually struggles to fully describe.
Really?
Yeah. Does the matter stay as neutrons? Or does the pressure become so intense that the neutrons themselves break apart, dissolving into a frictionless soup of their constituent parts?
The quark gluon plasma.
Exactly, a quark gluon plasma. We just don't know for sure.
The idea that after decades of observation and brilliant physics, the very heart of the object is still an enigma. I mean, some might find that frustrating.
But that uncertainty is the lifeblood of science. It isn't a weakness. It is the frontier. It is the very edge of human knowledge.
I love that.
These objects still hold profound mysteries about the fundamental nature of matter, gravity, and reality itself. They demand that we keep refining our instruments and our theories.
It's the reason we keep building better telescopes and more sensitive detectors. Because a neutron star isn't just a dead, static rock floating in the void, it is the ghost of a massive star.
It is.
A city-sized ball of pure, crushed matter heavier than the sun. It's a cosmic dynamo spinning hundreds of times a second, sweeping the galaxy with lighthouse beams of radiation, and occasionally colliding in a shower of gravitational waves to forge the heaviest, most beautiful treasures in the cosmos.
It really represents a profound historical and philosophical shift in how humanity views the universe.
How so?
Well, for millennia, our ancestors looked up at the night sky and saw the stars as eternal, unchanging, fixed, peaceful points of light on a dark canopy.
Right, just a quiet backdrop.
They had no conception that some of those serene points of light were actually the extreme, violently spinning corpses of stars that had died eons ago.
Or that the shiny yellow metal they dug out of the dirt and prized so highly was born in their invisible destruction.
Exactly. We went from perceiving a static, quiet sky to realizing we live in a dynamic, roaring, unimaginably extreme universe.
Which brings us all the way back to that tiny teaspoon of matter weighing 1 billion tons. It just proves that reality is far stranger, far more violent, and vastly more magnificent than our everyday terrestrial intuition could ever suggest.
Wonderfully said.
Thank you so much for joining us on this deep dive today, everyone. It's been a mind-bending journey, and we really appreciate you taking the time to explore the absolute terrifying limits of physics with us.
Yes, thank you for listening.
But before you step back into your normal, mostly empty space reality, we want to leave you with a final thought to mull over. If the heaviest, most precious things we own were forged in the invisible, violent collisions of dead stars, what other unimaginable treasures or phenomena might be echoing through the universe right now, just waiting for our instruments to finally become sensitive enough to hear them?